Today, I'm going to show you how you can use your TI-84 plus CE calculator to graph piecewise defined functions. Shown here is a piecewise defined function fx defined over three different domains. First, we have fx equal to x squared if x is smaller than 0, and that is shown by this blue curve here. Followed by fx equal to minus 1 when x is between 0 and 3, inclusive of the endpoints. And finally, followed by fx equal to x plus 1 when x is greater than 3. Our first step is to first check that the options are all ready by clicking on the mode button. Make sure that the function option is checked rather than parametric or polar or sequence. You need to have the function option checked. Quit. Click on the y equal button. From here, you can define your piecewise function by clicking on Math. Go down to option B, piecewise. Click enter and choose how many pieces you want. In this case, it's 3. Move down, click OK, enter. So now that is your template for you to define your piecewise function. First, we have fx equal to x squared. So to enter that, click on this button x followed by x squared, and then enter the respective domain. To enter the domain, we need to click on second, test, and then move on to conditions. Choose x smaller, which is option 2, enter. So in this case, it is x smaller than 0, so we click on 0, and then we move on to enter the next line. The next equation is minus 1, so we just click minus 1, and then right arrow again, enter the domain once again by clicking on second, test, move to conditions. In this case, we have x between 0 and 3, so we have to use option 5 here, which is this option. Click enter. Here we can enter the number 3, right? X is smaller than or equal to 3, and then we also have to enter the other number, which is 0. To enter 0, you have to insert the number 0. Click on second, insert, and click on 0. Okay, so it's fine. Let's move on to the other equation, the final equation, which is x plus 1. Right, enter the domain by going to second, test, go to conditions. In this case, it's x greater, which is option 4. In this case, we just enter the number 3, and there you go. So the function is defined, and then we can graph the function now. Take some time. So that is the graph of your piecewise defined function. Your TI-84 plus CE calculator actually allows you to change the limits of your x and your y axis. We can do this by clicking on the window button. Here we can define the range for your x and your y axis. So if you want your graph to look something like this one, which we have plotted earlier, in which case our x ranges from minus 3 to 7. So here I just click on clear, enter minus 3, and x maximum is 7. For y minimum, it is, let's say it's minus 2. Y maximum is 8. And then you can replot your graph. And this graph now looks very much like the original one that we saw. Now that you have defined your function, we can use it to find out the function values at certain x values. For example, what is the value of fx at x equal to 1? Or what is the value of fx at x equal to 4? So to do that, first we realize that by clicking on y equal, the function is defined as y1. So we have to take note of that later on when we enter our function. Now, second, quit to return to the home screen. To find out, let's say, what is the function value when x equal to 1, we have to look for the function by clicking on alpha, F4, select y1, which is option 1, open bracket, click on 1, close bracket. That will give you the value of -1, which is true, right? Because at x equal to 1, your function fx is actually -1. What about y1 at x equal to 4? By right, you should give us 5. Let's see. Now, to repeat the same computation but with a different argument, we just copy the above computation by highlighting the text, click enter, and then modify the argument to x equal to 4, click enter. As expected, that gives us 5, which is exactly what we see from the graph here. Our final exercise is to differentiate the graph at certain x values. If you were to analytically differentiate the original function, you end up with this new function at point x. Take note that at the points of discontinuity, meaning at x equal to 0 or x equal to 3, the derivative does not exist. Therefore, the equal sign is taken away. Now, to perform numerical differentiation on your TI-84 Plus calculator, we use the shortcut menu alpha F2 and click on option 3, n derivative, which stands for numerical derivative, so 3. We are differentiating with respect to x, so click on x, and then the function is y1. We can access that using the shortcut menu alpha F4, click on option 1, which is y1, and then we want to find out the derivative at, let's say, x equal to 1. From the graph, it's clear that the value of the derivative at x equal to 1 should be 0. Let's see if that is the case. Enter. Yes, so that gives us 0. Now let's compute the derivative at another point, let's say x equal to 4. That should give us the value of 1 as shown in the analytically obtained answer. So to do so, we copy the above computation by clicking the up arrow to highlight the above computation and then clicking enter. So the computation is repeated in the new line. Here we simply change the x value to 4. Enter. That gives us, as expected, the value of 1. Now, what if I were to compute the derivative at the points of discontinuity, for example at x equal to 3? Will I get an answer? Once again, copy the computation to the new line and change the argument to x equal to 3. Now, this gives us an unexpected answer. We know that the derivative does not exist at this point of discontinuity, and yet your calculator gives you a very large value. The reason for this is that the derivative is obtained numerically on your calculator, so this value is subjected to numerical errors. In reality, the derivative does not exist at this point, so do not be misled by your calculator to think that the derivative at this point x equal to 3 is 2500. This is not correct. Similarly, the derivative at x equal to 0 also doesn't exist. Let's see what is the value of the derivative obtained by your calculator at x equal to 0. So we change the argument to x equals 0, enter. Once again, it gives us the wrong answer. We know that the derivative doesn't exist at this point, so what you see here is subjected to numerical errors, and you should not trust a calculator when computing derivatives at points of discontinuity. We have come to the end of the tutorial. Thank you for watching the video. If you have any comments or questions, please write down in the comment section below. If you've enjoyed watching the video, please do consider subscribing to the channel. for more related videos in the future. Till then, see you.